In this lecture, we will define the fundamental loop. First, we define the set of loops at x0, is those maps from S1 to x, such that f of 1 is equal to x0. So giving such a map is equivalent to giving a map gamma from 0, 1 to x, such that gamma of 0 is equal to gamma of 1 is equal to x0. So thus we can also write so we will use both these forms. So basically, if you look, if there's Rx and there's x0, then Lx x0 is the set of all loops for x0. So we want to define an equivalence relation on Lx x0. For this, we introduce the notion of homotopy. Roughly speaking, we say two loops or two maps more generally are homotopic if one can be continuously deformed to the other. So there are several notions of homotopy. All small variants of each other. So the definition of homotopy which we need in this section is as follows. At f and g be loops at x0, we say f is homotopic to g if there is a map f from S1 cross I to x such that f restricted to S1 cross 0 is f. F restricted to S1 cross 1 is G. And for all t in I, F restricted to S1 cross t is also a loop at x0. So we denote this by F equivalent to G. So for example, a homotopy could look like this. So the first proposition we want to prove is easy. Equivalence relation. So homotopy is an equivalence relation on Lx x0. So proof. So we need to prove three things. F is equivalent to F. This is clear by taking f of x comma t to be equal to f of x. 2. You want to show that if f is equal to g, then g is equivalent to f. So for this, suppose we are given f from S1 cross I to x such that these three conditions are satisfied, and f restricted to S1 cross t for all t, then define g to x by g of x comma t is equal to f of x comma 1 minus t. So then it is easily checked that g is equal to f. The third thing we want to prove is that if f is equivalent to g and g is equivalent to h, then f is equivalent to h. So in terms of a diagram, we may represent a homotopy as, so let's say we have a homotopy f, this is between f and g, it's x naught at both ends. We have a homotopy g, this is between g and h, this is also x naught at both ends. So we can put these two together and since these agree on this closed subset which is the intersection of both these, that will imply that f is equivalent to g. But let's just write the formula. Define h of x comma t to be equal to f of x comma 2t, t lies between 0 and half. then one easily checks that H is a homotopy from F to G, F to H. So we define to be the set of equivalence classes. So we want to show that there is a natural group structure on I1XX0. So first we define the binary operation star on LXX0. So given two elements f comma g in two loops at x0, define f star g, again which is going to be a loop at x0, as of t, f of 2t, g of 2t minus 1. So basically it covers f at twice the speed from 0 to half, and then it covers g. So our aim is to show that the binary operation star descends to give an operation on equivalence classes. So we need to prove this lemma. Suppose f1 is equivalent to f2, then f1 star g is equivalent to f2 star g. Similarly, if g1 is equivalent to g2, then f star g1 is equivalent to f star g2. So proof. Suppose f is a homotopy from f1 to f2, then we can represent f like this. It's x0 here, x0 here. So we just add another so here on all the horizontal lines the map is G. So this combined thing will show that f1 star G is equivalent to f2 star G. So to write this homotopy explicitly is left as an exercise. Similarly, we can show that f star g1 is equivalent to f star g2. So as a corollary, we get that f1 equivalent to f2 and g1 equivalent to g2 implies f1 star g1 equivalent to f2 star g2. So the proof is simple. f1 star g1 is equivalent to f2 star g1, and this is equivalent to f2 star g2. As a corollary of the corollary, star descends to give a binary operation on the fundamental group. So we want to show that this defines, we will show a group structure on pi 1. So first we need to show that star is associative. So proof. So we need to show that f star g star h is homotopic to f star g star h. So what we will do is f So we will define a homotopy which on this line takes f over here, g between these 2 points and h between these 2 points. So more precisely, we define g from I to I by g of t is equal to 2t for t lying between 0 and 1 by 4, t plus 1 by 4 for t lying between 1 by 4 and half, and t by 2 plus half for t lying between half and 1. And define the homotopy So then h of t comma 0 is of t. So this implies this is just f star g star h. H of t comma 1 of g of t, and one can check that this is equal to f star g star h. And for each s, we have h of 0 comma s. So we have to put t equal to 0. This x naught, and h of 1 comma s of 1, and this equal to x naught. So this implies that for each s, h of thus f star g star h is homotopic to f star g star h, and the proposition is proved. So next, let's check that. Let C x naught from I to x denote the constant map. So clearly, C x naught is an element of L x naught. And we want to check that C x naught gives the identity element. So proof. So we need to check that F is homotopic to F star C x naught. So in terms of a diagram, we will construct the homotopy as follows. So on this line, we will cover F in this distance and the remaining to be C x naught. So the precise formula is as follows. Define G from I to I by So one easily checks that this gives a homotopy, and to show that F is homotopic to Cx naught star F, we will use a picture like this. So now define so this completes the proof of the lemma. So that these are homotopies is left as a check to you. And finally, we want to define the inverse. So for f in L x naught, define I of f in L x naught by f of 1 minus t. So if we have a loop f, then I of f is just traveling the loop in the reverse direction. And we want to show that so proof. So it suffices to show that f star I of f is homotopic to Cx naught, since if we put f equal to I of g, then we get I of g star I of g Cx naught, but I of g is simply g, and that will prove the second part follows. So the idea to show f star I of f is homotopic to Cx naught is as follows. So for S naught, let h t S naught be the path from x naught. It goes up to f of S naught and then returns to x naught along f. So more precisely, we define f of 2s t when t lies between 0 and half, and f of 2s minus 2st when t lies between half and 1. So we have defined h in two regions, and when t equal to half, it is clear that both definitions are equal to f of s. So H defines a continuous map checks, and easily checks that H is a homotopy between Cx0 and F star FF. So we have to show in particular, it is easy to check that Cx0 is HT0 and HT1 is equal to F of 2 minus 2t, and it has to be checked that this is equal to F star I of F at t. This is an easy check which is left to you. So in view of this, we have proved the following. The following theorem. The set Xx0 is a group under the operation star. The identity element is Cx0 and the inverse of F is IFF. So before we see some examples of computations of fundamental groups, some simple examples, let's just observe some more properties of the fundamental group. So the first property we want to see is that F from X to Y be a continuous map. Then there is a map F lower star from loops at X0 to loops at F of X0. So given by, so we have 0, 1 to X. Let's say we have a loop gamma. So I can just compose it with F. So if gamma 1 is homotopic to gamma 2 and F is the homotopy between them, then it is clear that F compose gamma is a homotopy between F compose gamma 1 and F compose gamma 2. So this implies that F lower star descends to give a map of sets and there is this obvious proposition which follows from the definition. Suppose we have two maps then G compose F lower star equal to G lower star compose F lower star. So the proof is obvious. So, but the main point is F lower star is a group homomorphism. So the proof of this is also very easy. F lower star of gamma 1 star gamma 2. Okay, so the stars mean different things, so one has to be careful. Is by definition F compose gamma 1 star gamma 2. This one checks easily is F compose gamma 1 star F compose gamma 2, and this is equal to F lower star gamma 1 star F lower star gamma 2. So this proves the proposition. So let's see an example, an application of this. So suppose I from A to X is an inclusion. Such that there is a map R from X to A, so that R compose A is the identity on A. R compose I is the identity on A. Then at the level of pi 1, we get maps and this is going to be identity pi 1A. So this would mean that if there is such a map R and pi 1 A comma A is a subgroup of pi 1 X. So we say that A is a retract of X if there is such a map R. So we will return to this example a little later. So some easy computations of the fundamental. So let us first check that pi 1 of a point P is just a trivial group. This is clear because in this case, the loops, so x is just a single point P, and the loops at P is just one map, which is a constant map. So obviously pi1 is also, as I said, it has just one point, and so this is trivial. Okay, so before we see some other examples, let's do this. Let's consider a slightly general situation. Suppose maybe we can do the examples first. Let's compute pi1 r, 0. So observe that there is a map f from r cross I to r given by f of x comma t is equal to x times t. And this map satisfies three conditions. F of x comma 0 is 0. F of x comma 1 is the identity of r, and f of 0 comma t is 0 for all t. So we claim that pi1 r comma 0 is a trivial group. So for this we need to show that given any loop f with f of 1 is 0, f is homotopic to the constant loop at 0. So the idea is we can just, so f is going to be some loop like this, and we can just multiply with time with t and shrink the loop. So define a homotopy f of s comma t is equal to t times f of s. So f of 1 comma t is equal to t times f of 1, which is 0 for all t. F of s comma 0 is equal to 0, and this is the constant map f of s comma 1 is equal to f of s. So we could have also written this homotopy as follows. F cross edit. Okay, so maybe we can use the notation f tilde here. So what I want to say is f is equal to f tilde compose f cross identity. So this proves that pi1 r comma 0 has only one element, because all loops are homotopic to the constant loop. So this is true. But now we will generalize this example as follows. Suppose we have an inclusion I from A to X such that there is a map and a map, not such that and there is a map F from X cross I to X such that F of say F restricted to X cross 0 is equal to identity of X F restricted to X cross 1 has image in A and 3 F restricted to A cross I is equal to, so let me write A cross T, identity of A for all T. Then we say that A is a deformation retract of X. So the map F continuously deforms X into A and is but keeping A fixed. At all times. So the proposition we want to prove let A be a deformation retract then I lower star from pi 1 A to pi 1 X A is an isomorphism. So proof. So let F restricted to X cross 1 is defined to be R. Then R is a map from X to A and R compose I is equal to identity of A. So this implies that from what we saw earlier, I lower star is an inclusion. So let us show that I lower star is a surjection. So let f from S1 to X be an element of P loop based at, say, A0. So consider the map. So since f of A0 comma t is equal to A0 for all t, we get that f compose f cross identity restricted to S1 cross t is in Lx A0 for all t. F compose when we restrict it to S1 cross 0, if we apply it on an element z comma 0 is equal to f of z comma 0, which is simply equal to f of z. Since f restricted to x cross 0 is identity, so this implies that S1 cross 0 is equal to f. And f compose f cross identity restricted to S1 cross 1. So when we apply it on z comma 1 is equal to f of z comma 1. This belongs to A. So if we take G to be the map from S1 to A, given by G of z is equal to f of z comma 1, then this means that f compose f cross identity restricted to S1 cross 1, we can write it as I lower star G. So this means that f compose f cross identity is a homotopy between f and I lower star G. So thus I lower star is surjective. So this easy proposition, using this we can compute Topology let X be a space which deformation retracts onto a point, then pi1 x comma p. So let's say onto a point P. So for instance, so let's just take several examples. So we can take the disk, we can take the origin, and then we can deformation retract it to the origin. So f of x comma t will then be x times 1 minus t. Or we can take the disk and we can take 1 and we can define f of x comma t. So this is my x, and we can go along the straight line joining x and t. So 1 minus t times x plus t times 1. Or we can take Rn and we can use the same over to b. F of x comma t is equal to x times t. So with 0. So this implies that pi1 t0 is equal to pi1 t1 pi1 Rn0. So all these are the trivial group. So let us end here.